Hello everyone, welcome to another class. Today, I will be teaching optical instruments and the microscope. And I hope that you are able to pay rapt attention, focus, and get the very best in today's class. So I'll quickly move on to the board and I will discuss. Get ready your notes and please pay rapt attention. Optical instruments, and then we talk about the microscope. Let me entirely share my screen so that we can get to the job. All right, let's go. Optical instrument and the microscope. Let's talk about some things about optical instruments. Let's make some points about them. Optical instruments, first of all. Optical instrument. Please take notes. Take these points down, read them, utilize them for your examinations. These are instruments that use, or that are used rather. Or let me make, sorry about that. Let me make the statement more concise. These are instruments that are used for magnifying an object or as an aided device for viewing an object. So please take note of that. They're used for magnifying an object or as an aided device for viewing an object. You can add to that explanation by saying they are designed. They're designed to focus images of objects either on the retina of the eye or on the film, or on a film rather. So we can say examples include microscopes and telescopes. So pay attention. Optical instruments, some examples are microscopes and telescopes. So we can make another point or two more points before we start discussing some concepts. Optical instruments make or let's put this one like this. Optical instruments that make objects viewed to appear larger are regarded as aiding devices. So they aid our sight. Let's discuss some concepts with respect to the eyes. Number one, let's talk about far point. Far point refers to the most distant. Excuse me for a bit. The most distant point the eye can focus. So take note of that. For the normal eye, I don't know if there's any such thing as an abnormal eye, but for the normal eye, don't worry, I'm using glasses, so no shade. No shade on those using glasses. I'm also a four-eyed person. For the normal eye, it is at infinity. So we say far point, the most distant point the eye can focus. For the normal eye, this point is at infinity. Okay, let's make some other points under this point and say the ciliary muscle, the ciliary, C-I-L-I-A-R-Y, ciliary muscles are completely relaxed. And the eye is at rest or unaccommodated. That is far point. Let's go to the next important concept with respect to the eye, called a near point. As for near point, the point where the eye is fully accommodated, or where the limit of accommodation is reached. The distance from near point to the eye is known as the least distance of distinct vision. The least distance of distinct vision, and is denoted by D. For the normal eye, that distance, D, is always 25 centimeters for the normal eye. So let me quickly explain the concept to you here. This near point, or let me talk about the least distance of distant vision. That distance between your near point and your eye. It means, let me give you the scenario of no matter the eye problem you're having. For example, I have an eye issue, but even though I take off my glasses and I place something 25 centimeters away from my eyes, no matter the problem, 25 centimeters away from your eyes, you should be able to see that thing. Do you get my point? 25 centimeters away from your eyes, you should be able to see that thing. So that's the meaning of the least distance of distant vision. Let's go straight into the next important point, that the eye ring. Eye ring. This is the best position of the eye when using an optical instrument. So you can also call it the point. It is the point where maximum light is collected by the eye. Take note of that. It is located is located at the image of the objective lens. Or let me put it like this, of the objective in the eyepiece. Just take note of this point and let's move forward. Still on this eye ring, in a microscope, the eye ring is at the point where a circular opening is made. And then in a telescope, the eye ring is at the exit pupil or exit port or eye pupil, which acts as an aperture stop. So keep that in mind. So let's talk about lenses. Or let's make a point. Let's make the point. Optical instruments are commonly made of lenses. The magnifying, let me just put a full stop here. They're made of lenses. And I said the magnifying power depends on their focal length. So the meaning of that is, this is it. Please try to discipline yourself to always take notes and read them. Don't just say, oh, it's so boring, they are just making points. No, these things can come out in your OBJ, multiple choice section of your exams. Listen, take notes, and reread them. Get the most essential points from them. That's why you're a student. So because I'm about to make a formula point here now, magnifying power of a lens, which is denoted by P, is always equal to 1 over focal length. That's what that point was talking about, that the magnifying power depends on the focal length. So take note of that. So this P that you see, which is magnifying power, it is measured in diopters. It's not an SI unit. So these diopters, and then focal length. So this is not an SI unit, but that's another unit for power, magnifying power to be precise, for lens. It's measured in diopters. Then focal length is measured in meters. So we can say power is inversely proportional to focal length. Inversely proportional to focal length. The meaning of that is that whenever you hear inversely proportional, it means as power increases, or let's say as focal length increases, power decreases. And then as focal length decreases, power increases. So it's just like opposite things happen to them. That's what it means to be inversely proportional. Take note of that. Let's make another point by saying that power, listen attentively and take notes. Please, no jokes. Power and focal length are positive for convex or converging lenses, and negative for concave or diverging lenses. Are you getting me now? Yes. Power and focal length are positive for convex or converging lenses and negative for concave or diverging lenses. Please take note of that. From here, you can see a special name for convex. It's also converging. And then concave lenses are also called diverging lenses. Please take note of that. Everything is important in whenever you are being taught in the class. Don't just say any part is boring since it's not calculation. No. These things come out in multiple choices. That's going to make, and they can even come out in your, theoretical questions. If two lenses of focal length f1 and f2, let's talk about this point now. If two lenses of focal length f1 and f2 are in contact, the combined focal length f can be found from their reciprocal sum. So yeah, we're about to get something, the generally called lens equation, mirror equation, of those things. If two lenses of focal length f1 and f2 are in contact, the combined focal length, they are saying, this is what they just said in that statement. 1 over f equal to 1 over f1 plus 1 over f2. They're trying to tell you that f is the combined focal length. So, and then f1 and f2 are the lens, are the focal length of the lenses that are being, individual focal length of the lenses that are being combined. Keep in mind again that magnification of a lens can be positive or negative. Positive or negative. Magnification can be positive or negative. Keep that in mind. So let's quickly talk about, and normally, as I go ahead, I'm going to explain what magnification is. We basically just touched, talked about power, magnifying power. But definitely you will see, as I go ahead in this class, you will see what magnification is. But I would like to talk about it for individual, different kinds of optical instruments. So let's see. Examples. Let's go practically into, let's go more detailed into examples of optical instruments. Yes. We can talk about, first of all, the simple microscope. Simple microscope. For a simple microscope, it is made up of, let's do it that way, one converging lens with object between the principal focus and the lens. Take note that for the simple microscope, the image is virtual, erect, and magnified. This is a very important point. For the simple microscope, the image is virtual, erect, and magnified. Take note of that, please. Yeah, let me. Okay. We have established what D is above, because I'm about to make a point. We said D is 25, that's like near point. D is equal to 25. Near point. I want to quickly state that the magnification for a microscope, a simple microscope, or let me write it this way. For a simple microscope, a magnifying glass, or hand lens, the magnification M is equal to D over F minus 1. So keep that in mind. So whenever you want to use this formula, in this case, D we have established, before I make the point I want to make, we have already established that magnification can be positive or negative. And then we said that okay, never mind. Let me just quickly give you a different set of this formula. When we have D as negative, keep in mind, we use this particular formula when D is negative, and M is positive. So when this is negative, you will get a positive M. So another version of the formula is D over F plus 1. This is used for positive D, and then M is negative. We have M equal to 1 minus D over F. And in this case, D is negative and M is negative. For your image at infinity, your magnification is simply D over F. Take note of these. Don't worry, as we solve problems, we'll refer back to most of these things. Please just take them down and take note of them. Let's quickly now go and talk about a compound microscope. We just talked about the simple microscope. Let's go ahead and talk about compound microscope. Compound microscope. Well, in a compound microscope, the compound microscope, we have two converging lenses of short focal length. Keep that in mind. We have two converging lenses of short focal length. Let's do it this way and say, but there is the eyepiece and the objective. Okay, let me put it like this: the eyepiece, and objective. So objective, that's two converging lenses of short focal length with object between F and 2F, that is focal length of the objective lens. Keep this in mind, just take note of it. The objective image is beyond 2F naught and less than the focal length of the eyepiece. Why? The final image is anywhere between 25 centimeters from the eyepiece and infinity. So you keep that one in mind, but also note that your final image, this is a very important point, your final image is virtual, inverted, and magnified. So this particular point here, take note of it. Virtual, inverted, and magnified. So you can also note that the final image is outside the lens. It's outside the lens. And nearer the object. Keep that in mind. We can quickly talk about something called the modified. Let me put that down. Number 3, modified compound microscope. So the modified compound microscope, here the final image is at the near point of the eye and within the lenses. So we can say the eyepiece. In this case, the eyepiece is also made from combination of lenses to reduce distortion. So why do we combine lenses to reduce distortion? Take note of that point. So for compound microscope, let's make a point. Compound microscopes. Yeah. M is equal to M1, M2. So the magnification, the combined magnification is equal to magnification of the eyepiece lens and the magnification of the objective. So we can always get that by doing object of image distance over object distance. So generally, let me establish. In that part of your notes where I wrote here, this was the point I was trying to establish. Magnification of lens can be positive or negative. Go there and write in bracket, magnification equal to V over U. Where, just find somewhere to write it. V equal to image distance. Then U equal to object distance. So just keep that in mind. So I'll just give you like 1 minute to establish that so that we can move forward. So coming back to where we are now currently in the class, talking about magnification for compound microscopes. And we are saying it is the multiplication of two magnifications. That is magnification of object. Let me use, instead of using 1 and 2, let me use like O and E, object and eyepiece. So that's like saying you are multiplying VO over UO times VE over UE. Take note of that. And that's like saying you can write the formula as, another way of writing this formula is VE over FE plus 1, VO over FO minus 1. So the reason for that is because we have 1 over F is another rule for lenses and mirrors plus 1 over V. So this is, take note of this. Take note of this formula too. Just keep it in your reservoir of formulas and take note of this other one. So let's move forward. Don't worry, those formulas become more, clear to your understanding as we utilize them. For now, take down the notes, memorize the formulas, and then when we start solving problems, you start seeing how they are next. Let's talk about the simple. We've talked about compound microscope, modified compound microscope. Let's talk about a simple astronomical, simple astronomical telescope. Take note of that. A simple astronomical telescope is made up of 2 converging lenses, of long and short focal lengths. So objective and eyepiece. So they're trying to tell us the kind of tool is still also, so it's kind of similar to the compound microscope. But we'll get to see some other things about it. So it's made up of 2 converging lenses of long and short focal length. And those converging lenses are objective and eyepiece. So let me see. Let me write it better. Sorry about that. So I can say these converging lenses are objective and eyepiece, where the focal length of objective is always greater than the focal length of eyepiece. So take note of this guy. It's just like saying the focal length of objective is always greater. So what's the usefulness of simple astronomical telescopes? They are used for viewing celestial or heavenly bodies, e.g., stars, moon, planets, etc. Take note of that. They're used for viewing what? All of those bodies. So another point I would love to make here is yes. Okay, let's talk about the magnification. Yeah, magnification. The magnification is equal to angle subtended by image at the eye over angle subtended by object at the eye. Take note of that. So another way you can write that formula. So this particular magnification is called angular magnification. Just take note of that. So when we have, let me call it MA. When we have ML, which is linear magnification is simply equal to focal length of objective over focal length of eyes, of eyepiece rather. So just take note of these formulas. We play along, play better with them. So I said this is linear magnification. So take note of that. We'll keep moving. We'll keep going. We're going to talk about a modified astronomical telescope. Mind you, the topic is optical instruments. You see some of them? Modified astronomical telescope. Or we say, another way of naming this guy is the simple astronomical telescope, which has normal adjustment. So modified astronomical telescope, or you say in normal adjustment. So just keep that in mind. So let's just talk about the characteristic here. We can say the focal length of objective and the focal length of the eyepiece, they coincide in their axis. They coincide in the axis. You can also say the separation or distance between lenses is equal to FO plus FE. Take note of that. By now, you should know that FO is like focal length of objective lens, and FE is focal length of eyepiece. So another important point here is angular magnification. Angular magnification for the modified astronomical telescope is equal to linear magnification. That is, they don't have separate formulas. is equal to linear magnification. And that is equal, they are both equal to FO over FE. Take note of that. So we have the next thing we'll be looking at as similarities. Similarities between the compound microscope and astronomical telescope. Similarities between the compound microscope and astronomical telescope. Right. So take note of these things. Number one, the eyepiece, also called ocular. So let me write that clearly out. Ocular. O-C-U-L-A-R. The eyepiece, also called ocular, functions as a magnifying glass in both instruments. Take note of that. Then final inverted image is produced in both instruments. So which does not matter. Final inverted image is produced in both instruments. Let's not add this part of is which does not matter. I wanted to make a point, but let me just talk about that point. Just say note. Compound microscope deal with tiny objects. Wow. Astronomical telescopes are designed for distant or heavily bodies and not objects on the earth. So get the point. Although this point is it would have been made in the next subheading, which is differences between compound microscope and astronomical telescope. Take note of that. Let me quickly put it in a tabular form. Compound microscope. Do I need to put it in the tabular form? I don't need to. I don't need to. Oh, let me just put it in the tabular form. Okay. We're repeating some things, but no, it's not. Let's just keep the structure right there. Like the first one we made before is that this is used for tiny objects. Let's use it is used for tiny object. This is it. It is used for tiny objects. Keep that in mind. It is used for tiny objects. While the astronomical telescope is used for distant objects. Let me make another point. It can be used for objects in the earth. It cannot be used, or let's put it this way, it can be used, it is used for objects, or let's say heavenly bodies. Heavenly bodies, e.g. stars, the moon, etc. The last difference I'll make is the fact that magnification for compound, it can be linear or angular. But yeah, magnification the magnification is only angular. So keep that in mind. Let's quickly talk about the next optical instrument, which is, we stopped at number 5. So this is going to number 6. That is the Galilean telescope. Galilean telescope. It is also called opera glass. And it has one converging lens. That's the objective. And one diverging lens, the eyepiece. So we discovered that how this differs from the compact telescope and the compact microscope and the astronomical telescope is the fact that those ones, they have like 2 converging lenses, which work as either the objective or eyepiece. But in the case of the Galilean telescope, It works with a convergent lens and a divergent lens. So one in this case is objective and the other one is eyepiece. So please take note of that. So the divergent lens is for inverting final image. So the first image, let's say it like this. So this will give you a very important point. The first image produced by the converging lens, which is the objective in this case, is a good acronym for, let's say, is real, inverted, and diminished. A good acronym for that is READ. Real, inverted, and diminished. That's the one produced by the convergent lens. Then the second image, or the final image, produced by the divergent lens, the eyepiece in this case, is virtual, erect, and magnified. Take note of that. Virtual, erect, and magnified. And then the acronym for that is VEM. VEM. So you see this point here, they help you answer questions about divergent lens and convergent lens. So please take note of it. You see this particular telescope, many times you've been hearing in this particular class that the telescope is used for heavenly bodies. But the Galilean telescope can be used on it. Because it forms an erect image, which is appropriate for a near object. Take note of that. Can be used on Earth, forms an erect image, which is appropriate for a near object. Another advantage of this guy is that it is cheap. It is cheap to make, and small in size. So I can call these 2 points that I just made, which is actually 3, because I can call small in size the third one. I can call them the advantages of this Galilean telescope. Why, if I want to talk about the disadvantages, I will say it has a small field of view. Take note of that. And then I will say it has poor magnification. You can point out that here the separation, if you want to calculate the separation of the lenses is given by focal length of objective minus the focal length of the eyepiece. Take note of that. And when you want to calculate the magnification, you simply do ratio of the focal length of objective to the ratio of the focal length of the eyepiece. Take note of those points. The next optical instrument we'll be looking at is the terrestrial telescope. The terrestrial telescope. And this particular one is very interesting because so far we've been looking at two things in a group of twos. I mean, we're looking at pairs. I mean, what I mean by pair, P-A-I-R, that is, it's either we're talking about two converging lenses or one converging lens and one diverging lens, which still, that's two things. But then the terrestrial telescope is unique because it makes use of three lenses. But all the three lenses are converging lenses. So there is still even an additional middle lens. And that lens is called the inverting lens. Okay, let's talk about it in your write-up. So I'm going to state that these are three converging lenses with the additional or middle lens called an inverting lens. Take note of that. Normally we have three lenses and then an additional middle lens called the inverting lens. Take note of the fact that the additional lens is placed at a distance to F from the objective image. And it extends the separation between the lenses or the length of the telescope by 4F. So take note of that. Here we have the same idea. What I mean by the same idea is that this telescope can be used, this telescope can be used on Earth, but it is not cheap. It is not cheap because of its big size. It is longer and heavier than most optical instruments. Take note of that. Then before we move to the next optical instrument, I would love to state, I'd love to talk about the fact that the separation, when you are asked about separation of the lenses, in the case of the terrestrial telescope, the separation of the lenses is given by the formula FO plus FE plus 4F. And always keep in mind this particular formula. So make sure that you take note of that. Don't worry, we'll exhibit some of these formulas as we test out questions. So don't be bothered for now, just keep them in your reservoir. Keep them as your arsenal. I mean, when you keep your formulas in your brain, reserve them there. We'll move straight to the next optical instrument. Let's see. I will talk about two more before we call it a day in this class. Then I'll continue in the next class. Let me see. So yeah, I'm going to talk about the binocular. The binocular. This is a short telescope comprising of two astronomical telescopes. So the binocular is made up of two astronomical telescopes. Each of them has two right-angled, each having, or let's say, each with two right-angled isosceles prisms between the objective and the eyepiece. So please take note of that. What will happen is that I'm going to stop here for this class, and then we'll proceed to other optical instruments in subsequent classes, particularly on this topic. So in today's class, I'll just have a review. We've talked expressly about what an optical instrument is, and we said it can be used for magnifying an object or as an aided device. It particularly said those of them that are aided devices, they make objects viewed by them to appear larger. Then we started talking about important concepts like the far point. Here we said the most distant point where the eye can focus. And then we mentioned the near point, where we said the point where we have full accommodation. That's why I say fully accommodated, or where we have the limit of accommodation. That's how to read. When you are reading, you now start picking, as you're making something, you are picking the most important things there. And then we say for the normal eye, the least distance of distant vision is 25 centimeters. Where I explained that no matter your eye problem, if you remove that glasses of yours and you place something 25 centimeters in front of that eye, you should be able to see it. Then we went to the eye ring, and yes, we gave his own definition: best position of the eye when using an optical instrument. Then it goes on and on and on like that. And then we started looking at formulas which you are meant to keep in your reservoir of formulas. And so we'll meet next class. Make sure that you read. It is your duty as a student to study. Nobody can do that for you. So I'll see you in my next class.